Morning, team. All right, as promised, the good news is you don't have to learn anything new today, but I would like to just give you a chance to practice and I don't know, soak on this concept a little more. I mean, overall, everything we've talked about now in chapter 4, this is 4.4 today, is really just one question on a test. And it might look something like this. What if, this is kind of a cool one. So I'll just say the big picture of how to graph a crazy function and how calculus can help you with that concept. And so let's take a look at this example. This is a relatively nice one, but it's not super nice. And it also is kind of cool because it represents a model of something in the real world that's kind of cool. So that's the other thing. So let's say, and notice it looks not terrible to start with. So I'm going to give you a second to get a head start on that. What is the graph? What would the derivative be? And really the two things I'm going to ask on a test would be, one, find the maximums and minimums, however many of those there happen to be. And this is the, if you will, the algebra I'm going to want to see. And then the second one would be the inflection points. Inflection point or points. And I have to be a little careful on the test to make sure that this isn't too involved. The algebra of this isn't too involved. And so, as I hope you understand, the maximums and minimums are found when the first derivative is equal to 0, and the inflection points are found when the second derivative is equal to 0. So that's the algebra that I've got to surmount. So let me give you a second to get a head start on that. I'm not going to give you much of a head start here. So 18x divided by 2x squared minus 4x plus 5. So you should be thinking quotient rule. And so the derivative is derivative of the top times the bottom left alone minus the top left alone times the derivative of the bottom. That's not too terrible. All divided by the bottom squared. Well, it's already a squared equation, so now it's even squared beyond that. That's kind of messy. And then if I clean up the top by, in the order of operations, multiplying before I add and subtract, if I multiply the 18 into the first expression, I get 36x squared, and 18 times 4 is 72, and 18 times 5 is 50, and 40, which is 90. And then minus 18x times 4x is minus 72x squared, and then minus 18x times minus 4 is plus 72x. All over my denominator. And then finally, I guess I could say, and this is something I want to make note of and keep track of, 36x squared minus 72x squared is minus 36x squared. And then the 72x's, there's a minus and a plus, so they're gone. And so plus 90, all divided by our denominator, which I'm now going to copy. And so this is something I definitely want to keep track of. I want to use this. This is something I want to note on your test. You might want to note that to me as well with some kind of a box or something. All that work. And so now I found this derivative. And so now I can set this equal to 0. And as you know, if I set this equal to 0, the denominator doesn't even make any difference. And so I'm really just saying when is negative 36x squared plus 90 equal to 0, which really means if I add 36x squared to both sides, 36x squared equals 90. And if I divide both sides by 36, I get 2.5. So I could say x equals the square root of 5 halves and have it perfect. And remember, x can be plus or minus. So really what I get here is x is approximately plus or minus 1.58. And so here's where I want to use Desmos, like just to save some time, because remember what it means now is I know that x is 1.58, and so I just need to go back here and plug 1.58 into that expression to see what y comes out. But remember, on a test you want to be checking this stuff anyway, so it's kind of a cool idea to go into Desmos, and maybe I'll even just graph them at the same time. So I got 1.58, and instead of asking what it is, I'm going to graph it and ask it what it is at the same exact time. So notice, I know that's a maximum or minimum, and so I got 7.74. I didn't have to work at it. I'm using technology to give me that answer. Notice in this case, I didn't turn the graph on because I want to, I don't know, try to do this as much in my brain as I possibly can. So I left the graph turned off, but I'm using the equation to plug the number back in for me because I'm lazy and I don't trust myself to make dumb mistakes. So let's also get, while we are at it, the other point. So now I have apparently like a minimum and a maximum. And I think I'll make them both red because we're going to go back and hunt for some inflection points too. So, okay, cool. So more than welcome just to type that into your regular calculator on a test, because this is calculus. I don't need to see any work about you plugging 1.58 back in. That's kind of a waste of your time, I like to say. So I made those red, so I guess I'll make them red here. So I have maximums and minimums now. I don't know which is which, but at 1.58, 7.74 we just saw, and negative 1.58, negative 1.74. So that's kind of huge. Like those are two really helpful points if I'm trying to graph this. So that wasn't terrible. The algebra wasn't terrible. I just ended up solving this squared equation. Not so bad. All right, let's proceed to inflection points. Inflection points is when the second derivative is equal to 0. So this is why I highlighted the first derivative, because now I need to take the second derivative. And so again, I see quotient rule. So quotient rule says the derivative of the top which is negative 72x, times the bottom left alone. That's not good because that is squared. Derivative of the top times the bottom left alone minus, let's see, I'm going to try to squeeze this onto this. Minus the top left alone, negative 36x squared plus 90, I guess I'm not going to make it, times the derivative of the bottom. And the derivative of the bottom is kind of a pain because it itself is a chain rule. The derivative of junk squared is 2 times the junk now reduce that exponent by 1, so it goes from 2 to 1, but I'm going to take that off because it looks like a derivative, times the derivative of what's inside. And so the derivative of what's inside is 4x minus 4. All divided by the bottom, the denominator, squared. Well, it was already squared, so now it's to the 4th power. So this seems very terrifying. I'm writing too large. But maybe you notice something really cool here that would save you a whole bunch of trouble algebraically. First of all, notice there's a bunch of junk here and then a minus sign, very important because that separates it. And then a bunch more junk over here that's all multiplied together. Notice both of them have a 2x squared minus 4x plus 5. This one also has one, and there's one on the bottom too. Does it make sense you could divide out one of those from the top and the bottom? That would algebraically be a really cool thing to notice. If you just multiplied that top out and made a big mess out of it, you wouldn't notice that anymore because that kind of whole thing would go away. So this is a cool thing to notice. And also this makes this maybe a little hard for a test question because, would you notice that? I don't know. I mean, it's a lot to ask of somebody, I guess, algebraically. But maybe so that it's a little more obvious that that's the case, I'm going to simplify this a little bit first. And I'll write a little smaller this time. So let's see, f double prime of x equals, and notice that first expression, I can't really simplify it much. So I just see negative 72x times 2x squared minus 4x plus 5 squared. But then let's multiply out that stuff on the bottom a little bit. I guess I could distribute the 2 into the 4x minus 4 and get 8x minus 8. And then there's a negative 36x squared plus 90. And then there's 2x squared minus 4x plus 5. So I didn't clean that up much, but maybe you see it now. Maybe it's a little easier to see it now. So I'm saying I could divide them out. This one would be gone. I would lose one of these, and then this would go down to a 3. Like, wow, is that ever going to save me some time to notice that? I guess that's what I'm getting at. So now let's multiply this out. Again, I've got to use this. I've got to set it equal to 0 and solve it. So I'd like to clean this up as much as I possibly can. So now that there's only one of these 2x minus, I can just distribute that 72 in. So 72 times 2 is 144. X squared times x is x to the 3rd. 72 times 4 is 288. So it's positive. Negative 72 times positive negative 4 is positive 288. And there's an x and an x, so that's x squared. And then 72 times 5. 70 times 5 is 350. 2 times 5 is 10, so I guess that'd be 360. And there's an x there. So there's that distributive law done. And then I've got 8x times 36x squared. My calculator says 8 times 36. I don't trust myself, is 288. And so that'd be negative 288x times x squared, negative 288x cubed. But there's a minus out in front of it, so it's going to change the sign of it. Very dangerous to kind of do this all at once. I'd be smarter just to multiply this out and then change all their signs. Actually, I think I will do that because I don't trust myself. So that's a negative. So I'm going to defer this negative till a second from now. And then 8x times 90, that'd be 720x plus 720x. And then 8 times 36, I did that a minute ago. Negative times a negative is a positive, so that'd be 288x squared. And then finally, 8 times 90 is 720. That'd be negative 720. Now I'm going to go back and apply. I'm going to switch all those signs. So this becomes a plus, this becomes a plus, and both of these are negatives. Super easy just to make a dumb math mistake there. And that's all over my 2x squared minus 4x plus 5. And remember, I really don't care what's on the bottom of this because I'm setting it equal to 0. That's my purpose here. Although I'm going to show you something kind of cool in a minute. So now I'm going to collect all these terms together. And I wonder on a test, there's going to be some algebra in this section because I want to give you a graph that's kind of cool. It's got some maximums and minimums. It's more fun if it has, 2 or 3 of these things. But man, there's a lot of room to make a dumb math mistake here. I almost want to say the chances of not screwing this up are really small. Like, am I going to be able to see your work? So I'm going to be really careful here and say, okay, what do I have for x cubes? Well, there's 1 and there's 1. Okay, so my f double prime x then. So negative 144 plus 288 is plus 144. So there's my x cubed terms. X squareds, I'm going to mark those in kind of a different way. I have plus 288 of them, minus 288. That's really good news. There's no x squareds. That's cool. And then my x terms, I'm going to point at them. Minus 360 minus 720 is minus 1,080. And then there's that positive 720. So I'm going slow, and I actually don't think I screwed this up. Pretty sure I didn't blow this. And so again, this is a neat place to kind of stop and take stock of where you are. Like, I found a derivative. I found a second derivative. Now this is not good. What's not good about this? I haven't blown it, but what am I going to do next to find the inflection points?
Set it equal to 0?
Yeah, set it equal to 0, and because that only means the top is equal to 0, but this is not good. What's not good about that equation?
Because it's cubed, right? And finding a cubed equation set equal to 0 is really hard.
Yeah, it's cubed. So here's an extra credit opportunity for you. Go investigate online using Google. Google search like the history of people trying to solve cubed equations. You were never taught. Well, there's a quadratic formula that automatically solves squared equations, but is there a cubic formula? Historically, this was a rabbit trail that mathematicians ran down, and there's not a way. Like, that's the short answer. Well, there's a way if it's really narrowly defined, and then people have went very deeply into this, and so there's some really interesting stuff about cubed equations. So you kind of can, but you kind of can't. Now, you did do this in Math 111, but it was because somebody made these problems up really carefully. So I'm going to erase this bit. But if this, for instance, factored to x minus 2 times 7x squared plus 6x minus 9, does it make sense? This one would say x equals 2, and then this would give us 2 answers using the quadratic formula. And so it turns out something called the fundamental theorem of algebra, that's quite a statement, the most basic theory of all of algebra, the most basic truth is that cubed equations have 3 answers. Squared equations have 2 answers, cubed equations have 3 answers. And so if this problem was canned and it was factorable, then we'd have 3 answers, and one would be 2, and then the quadratic formula will give us the kind of the 2 decimal ones. But this was only possible because we were able to factor it, and that doesn't happen in a real problem, and that's what happens here. This problem is not factorable. Like, I just made up a graph, and so you're not going to get nice whole numbers. So this doesn't work, and that's why I'm saying go investigate the history on that a little bit. And what I'm after, like as far as the points are concerned, do it because you're interested, but as far as the points are concerned, copy some statements that you find online out, and then just type a couple of things to me, like, this was interesting, I didn't realize that was true. Just tell me a couple of things that kind of give evidence that you didn't just go copy a bunch of stuff and then send it to me and you didn't even read it. And don't go crazy. Like, I'm going to give you extra credit for just find, as soon as you find one thing that's interesting to you, stop. I don't want this to turn into 2 hours, but people went down this, here's a reason. Like, we have a reason now to solve a cubed equation. You did not have reasons in Math 111. They just said, let's try to solve this. But it's like, as a result of graphing this, we want to find these. And notice it's also telling us right now, this graph's got 3 inflection points. Well, you may remember from Math 111, there are 3 answers, but one could be real and the other 2 could be imaginary, 2 imaginary answers. And so maybe it only has one inflection point. But again, I'm not making this up tricky. This was kind of a cool problem. It has 3 inflection points. So how are we going to solve this? Well, in Math 111, we cheated. We cheated to solve this. And in particular, this is a really weird place to cheat, because in order to solve this, and I can't give you a question like this on a test. I don't want this kind of thing to happen. I want this equation to be squared, meaning I have to come up with graphs that only have 2 inflection points. And so I got to play around with this a lot. I want the graph to be interesting, but I don't want it to be so interesting that we end up with what's happening right now. So I think this is good for your thinking, but it's not good for a test question. So what you may remember, and I hope you remember from Math 111, is we said, okay, well, let's cheat and use a graph to do this for us. And so instead of saying equal to 0, we'll say let's equals y, so that now we can actually stick it on a graph. But if we did this, then where are we looking on a graph? Where are we looking? Well, we need to look where y is 0. Where is y 0 on a graph?
At the x-intercepts?
Yeah, any place the graph hits x, the x-axis, then that's a place, that's the points on the graph. Now remember, there's no graph here. This is not equal to y. This is just a brilliant idea to set it equal to y. And because we live in an age of technology that'll graph this for us, then we can look and see where does this hit the x-axis, and we're going to cheat and get our 3 answers. Now, the thing that's extremely sort of dumb about this is the whole point is, the original point of this was to try to find the graph of that intelligently. And now we're basically having to graph in order to find a graph. So it's kind of like, yeah, this is dumb. Just graph it in the first place. Do you see what I mean? So we're learning how to think here, but notice it's kind of funny that we're having to use a technique of graphing to graph something. It's like that kind of defeats the purpose. It's like trying to define a word that you don't understand and using the word in your definition. Can't do that. So let's go to Desmos and stick in not 0 equals, but y equals 144x raised to the 3rd minus 1080 x. There was no x squared term, and then plus 720. So for now, let's just turn off these other graphs so that we don't get confused by what we're looking at. There's nothing on here except for this graph. And so fortunately, Desmos I was going to say, usually it finds these for me. There we go. So Desmos is so much better than your graphing calculator, because it kind of intuitively says these are interesting points, and so I don't have to use the graphing calculator to go find them. But notice it says indeed, yep, there's 3 answers to this. So negative 3.025, 0.716, and 2.31. Those are the x's that work in that cubed equation. That's really cool. So
So how were people able to program this to solve something that we can't solve?
Yeah, that's a super interesting question. And as it turns out, that lives, the answer to your question, Felix, lives in this chapter of the book, which is you have a calculator that finds zeros. You may remember that where a graph hits the x-axis where y is 0 is sometimes called a zero. So in the second calculate button on your calculator, you can hunt for zeros. And so it turns out calculus is built into your calculator. So I'll be showing you that very shortly. That's a great question, Felix. Like, what's the magic? How did the calculator know to do it? Keep in mind too that what we just got is the rounded off to 3 decimal place answer, but the real answer to this, in a sense, nobody actually knows, because it's a decimal and it goes forever with no pattern to it. It's an irrational number, and so it's weird that we're saying we got an approximation for this, negative 3.025. I guess I'll call it 3.03, and 0.716. So I'll just call it 0.72, and it was 2.31, and so those are definitely approximations. And so the argument could be made, nobody knows what the answers really are. We just know approximation form. And so again, now I need to find the entire point. So, in order to be able to say I found my inflection points, I know that 3.03 is one of them, but there's y's that go with these. 0.72 is another one. There's a y that goes with that, and 2.31. I got to find the y's that go with these, but rather than plug that back in myself, as we did a minute ago, I don't want to go clear back to here and have to plug this in myself. But remember, we're taking advantage of technology that ancient people did not have. Like, you'd have to go, well, you get to put two, and again, I would just ask you rhetorically, could you actually do that if you had to? Can you take 18 times 2.31 by hand on a piece of paper and get an answer? Can you square 2.31, multiply it by itself, and then multiply by 2? Can you actually produce an answer to this? And notice you're going to get decimal over decimal. Can you divide decimals? Like, could you do this by hand if you had to? It's almost like an archaic skill anymore. Half my education was before calculators at all existed. I think I was in like the 7th grade when the first just cheesy multiply 2 decimals together the calculator came out. So I'm pretty good at this because I suffered uphill both ways in the snow, I think is how the phrase goes. As a kid, so I can still do it, but I bet some of you probably might screw that up a little more because you weren't sort of forced to do it as much as I was. I don't know if that's an advantage or a disadvantage. But again, I want to graph these. I don't want to just know the y values. I actually want to graph them. So I'm actually going to go in here and do what we just did a second ago and say, let's see, when x was negative 3.03, then what y value comes with that? So we're just going to let technology do it for us, which is awesome. So there's the y, negative 1.54. So I'll write that down on the notes in just a second. The other one was 0.72. Man, this is cool stuff. Looks like I just spazzed out with what in the world is wrong with me? I cannot function. There we go. Finally. So 4.11 approximately, and then last we had 2.31. See if I can not screw this up so bad this time. 2.31, comma, F, start a parenthesis, 2.31, close those parentheses. Oh, much better. So I don't need this graph anymore, so I'm going to get rid of it because that was annoying. And then the second thing that's kind of nice is let's change all these colors because there's a whole bunch of junk going on here. Let's just make all these inflection points black so that we aren't as confused. And also I'm going to turn those labels off because I'm a little confused. But if you stare at that now, knowing that the red is a maximum and minimum and the black The blacks are trends. What are inflection points again? What's
They're the point on a graph in which the direction of it switches.
Yeah, the concavity. In other words, whether it's concave down or concave up, there's a transition from concave up to concave down at those inflection points. So this is a really complicated graph, and these 5 points are all it takes to actually make a really good graph of this, as long as you know what they mean. And so let's do this. We're going to use that in just a second, these, but I don't really need that. So I want to just make it so that when I bring over, we can see everything. There, we see everything. So take a picture, bring it over. So I want you to stare at this beauty for a second and see if you can picture the graph. I'm going to crop it a little bit so I can make it as large as possible, as I often do. Oh, that is beautiful. So just so it's written down in the notes, I saw that negative 3.03 came out with negative 1.54 as its y coordinate, and 0.72 came out with about 4.08 for its y coordinate, and 2.31 was 6.64. I'm sorry, 6.46. So armed with these 5 ordered pairs.
Actually, your y coordinate for your second equation was 4.11 approximately.
4.11. I have a more accurate answer sitting in my notes, so I'll put what you said. I used 0.716 when I plugged it into my notes, so my answer is a little bit more accurate, but right around there. And again, to that end, estimation is totally fine. Like on a test, I'm not going to go -1, you're not accurate enough. Round it however you want. I'm not going to say round to do decimal places or any of that. Just round it however you want. I would say 1 or 2 decimal places makes sense. It's a little too cumbersome if you go much beyond that. So naturally, let's think out loud for a second. Naturally, if I see one maximum and a minimum and one is above the other one, don't you find yourself thinking it must, wouldn't you sort of be happy if it was the top one was the maximum and the bottom one was the minimum? Like that's kind of what you would think would be the case. And why does this inflection point here kind of agree with that? Why does it agree? Well, do you see the transition there from concave up to concave down? I mean, right through here wouldn't it be concave up, and then someplace in here there'd have to be a transition point. So that's what that inflection point represents, is a transition point to concave down. And so that looks good. What about over here? Does it go like that? Is that what happens? Why is that not true? Why could that not be true?
Wouldn't the inflection point in state, because you already have an inflection point that means it's concave down, so wouldn't that inflection point mean that's concave up?
Yeah.
Because it switches.
To the right.
Like right here, basically these inflection points say it's concave down, and so this can't just continue to be concave down. That's denying the purpose of an inflection point, right? It's saying, no, there's a transition to concave up, and so what it must look like is maybe something more like this. Is it, see how that transitions to concave up? Now, it could look like this. Well, it can't look like that, right? Why can't it look like that?
You would need another maximum or minimum point.
Yeah. For it to turn around, wouldn't you need a minimum point right there? And again, we found 1 maximum, 1 minimum. There's not 3. So the fact that we found 2 is cool, but it also means it's not 3. So it actually can't be that one. So it actually must be that one. It stays, there's not a maximum or a minimum over there, and it stays concave up forever. So way out there someplace, does it turn downwards out there? It can't, because then there'd be another inflection point. We found 3, there's only 3. So if you really understand what an inflection point is, I actually know that graph looks like that. Now, do I know where it levels out? Do I know it levels out against 5? Or does it actually come down and level out against 3 or something? That I don't know. I'd have to plug some points in to see. But basically, I know it must look like that. Well, what happens on the left side then? Remember, those are points on the graph. Like the graph has to hit them. And notice I've got it drawn like it's like coming up in the air over here. I have it drawn kind of like it's going up like this. Well, it's got to hit that black point. So how's it going to hit it and transition to a different concavity? Well, it has to continue to be concave up through here, right? Like it's concave up the whole time. So the red point is a minimum. So it's the bottom, and yet it continues to be concave up. So maybe it looks like that. But again, it can't continue to be concave up because that would mean the inflection point hasn't done a job. It hasn't changed its concavity.
Could you do kind of like at the end of your graph, it kind of levels out? Could you do that except coming from the bottom? So it kind of levels out and then all of a sudden switches?
Like this?
No, so you're coming from the bottom, you're going up, and then you're leveling out and then going up.
Coming from the bottom. You mean the red point is the bottom?
Not exactly. So you're coming from the bottom left-hand corner, coming up, kind of leveling out, and then going up.
Something like this. Is that what you were getting at?
Yeah.
I wish I could allow you to write on this, but I don't know how to do that. Would that work? Is that a possibility?
Never mind. That doesn't work.
Why not? You're right.
It is right.
Wouldn't you need another maximum point? Because
yeah, does
it kind of dips down?
For it to switch like that, that black point or some point around there would have to be another maximum or a minimum. And so it definitely could do that because it does transition here. Like this part is concave up and this part is concave down. But by doing so, you'd be saying, oh, there must be a third maximum or minimum point. And again, the math said there were only 2. So it's just kind of cool what you can know from this. So actually it can't do that. So it must look more like what I have drawn. But as I said, I don't think we've practiced enough that I think you just learned something, I guess is what I'm saying. Now, again, we live in a world of technology. We're going to check this against the real graph. But if you actually really understand what's happening, it would have to look like that.
What does this model? Because in the beginning you said it modeled something. What does this model?
Good question. I'll show you that in just a second. So let me just highlight, let's just stare at this graph and highlight a couple of things first, and then let's talk about some other things. And so let's see, what does this mean? Well, would you agree that from here to here, so the kind of things that you would see in, say, a homework assignment, and I could even do this on a test. I don't know if I'll do this on a test, but would you agree from there to there, F prime is positive? The slope is positive everywhere in that yellow area. And we say that is kind of code for the word increasing. So your profits or whatever are increasing all through that area right there. That's all increasing. And so you would say that mathematically by saying, well, that happens from x is negative 1.58 up to x is positive 1.58. Since that's what those maximum minimum values were from red point to red point. So the maximums and minimums separate the graph. There's like 2 separations here. One separation is where is this graph increasing? Where is it decreasing? So it's increasing. It has a positive slope from that minimum down there at x is negative 1.58 up to the maximum, which is x is positive 1.58. And then you would say it is decreasing here and forever and here in forever. Every place in there, the slope is negative. And so you need to see maximums and minimums as transitions between increasing and decreasing. And so that's why I knew the left part of this graph over here, that's why I knew the slope there had to stay negative forever. Otherwise, if it switched from negative to positive, then that would mean there's another maximum or minimum. Does that make sense? So f prime of x being negative, that is the same as decreasing, which really just means it's a negative slope. And so how would I say that? Well, it's from negative infinity all the way up to that 1.58 number. And then again, from positive, I'm sorry, that was negative 1.58. And then up from the positive 1.58 all the way up to positive infinity, like that's the interval, that's the x values. So I just want you to be able to speak the language of math. I mean, it's just kind of cool to note. So in a very real sense, I think I'm going to erase this because it's going to make this confusing, but in a sense, maximums and minimums, that since there was 2, it divided the graph into 3 different kind of regions. So from here to the left, the graph is decreasing forever. From here to here, it's increasing. The profits are going up, or in this case, drugs in your bloodstream are going up. And then from here to here, forever, it's going down. So the maximums and minimums divide the graph into 3 different regions. So now let's consider what the inflection points do to the graph. And I think I'm tempted to, I should probably copy this and do it again. Actually, I don't think I will though. I think I'll just write right over the top of this. Let's choose a different color. So the inflection points also divide the graph. There's one, and there's one. And what do you notice? Like what division do inflection points make? What's between each of those?
Maximum or minimum?
Not maximum or minimum.
Tells you when the concave cavity is going up and when it's about to switch to going down.
Yeah.
Like if it was like a stock market or something.
Yeah, it's concavity. It's like, how is it changing? So it's concave down there. It's concave up between here and here. It's concave down between here and here, and then concave up from there forever. Do you see what I'm saying? It's like a totally different division. So in this area, since it's concave down, that means f double prime of x is going to be a negative number everywhere in there because it's concave down. It's telling you that the rate of change is changing negatively. Again, I don't think this is obvious. In here, and I'll show you this in a second in a kind of a cool way. Here, between there, it's positive. In other words, the rate of change is changing in the positive direction. Down here, you have a small slope, a small positive slope, but then it's getting steeper and steeper and steeper. The change of your slope is positive. Your slope is getting better and better and better. Once you jump into this range, you're back to the second derivative being negative again, concave down. Out here, the second derivative is actually positive again. So there's like 2 ways to divide the graph up. I mean, isn't that kind of an interesting way to look at it?
Could you use these points to work backwards to find your function for your graph?
Yes, that'd be difficult. In other words, if you took data in the real world, like somebody had drugs in their bloodstream and it peaked, and you wanted to work backwards to try to find an equation that would model it so you could use it to predict the future. Yeah, that's hard, but yeah. Let me show you something kind of cool just in light of this. Like, try to hold this in your brain a little bit. Notice the orange outline. We had a negative first derivative to here, we had a positive first derivative to here, and then we had a negative first derivative to here. Just want to show you something that doesn't come up very often, but it's kind of a cool skill to have. So I'm going to stick this in the graphing calculator real quick. On y equals, on again, y equals. So I just typed in here before class to save a little time. This was our second derivative. Do you see that? 144x cubed minus 1080x plus 720 all over jump to the third power. That was our second derivative. So this is telling us concavity. That's what you want to think of. If this is positive, it's concave up. If it's negative, it's concave down. Now maybe you've never messed with this before, but this is a great place to do this, like to see a bunch of ordered pairs. So what I'm going to do is go into second table set, like control the table. And where do I want to look? Well, our graph kind of, let's see, -2, -3, 4, 5, 6, maybe -6. Seems like there's a backspace. Why can't I remember this?
It's the delete button next to the left arrow.
Is there? I thought there was another way to do it, but I don't know, maybe it doesn't matter. So the way I have this set up is to start the table. I want to start it. This is what this means. It starts at an x value of -6, and then the change in the table is 1. So the next x value will be 1 higher, -5, and then -4, and then -3, and -2. And it'll just go up forever. And so what I'm going to see is a whole bunch of x, y's for the second derivative. So now I say table. So there's table set. I got it set up like I want it. And now let's go to table, second table. So what I want you to pay attention to here is just the sign of the, remember this is what this is telling you is y1 was the second derivative. In other words, is the second derivative positive or negative? I don't care what the number is. It's just, is it positive or negative? So notice from x is -6 up to -4, it's always negative. Oh, that's concave down. So then it switches to positive. Oh, it's concave up. Well, where's that switch right there? What's somewhere between -4 and -3 was the switch? Wasn't our inflection point at -3.3? Was it -3.3? Something like that. -3.03, that's what it was. So it's concave down, and then when it hit -3.03, it became concave up. Do you see how you can see, like you could actually understand this graph without ever graphing it at all? I mean, I want to graph it because I want to see it in action, but notice now it's positive, and let's arrow down and look at it a little more. Notice it's positive from all the way down here, so it's concave up, and then it's suddenly concave down. What's the transition right there? Well, remember that was 0.72. 0.72 was the actual inflection point, and so at 0 it was positive, but then when it passed 0.72, now it's negative. And so do you see how you can see the concavity here? So here it's concave up, and then all of a sudden it's concave down, a bunch of negatives, and then it's concave up again. And notice it's concave up forever. So all I have to do is see the positives and negatives, and I can tell the graph is concave up or concave down. That's kind of cool. Let's take a second and just look at the slope equation in the same context. The slope equation was -36 x. I have to insert a squared, insert squared, -36x squared plus 90. Delete 90. And the bottom was over squared. And so this is, again, I'm not looking at the graph of this, but that was our first derivative. So our first derivative doesn't tell us concavity, it tells us slope. Is it positive slope or negative slope, which is kind of code for increasing and decreasing. If I go back and look at that table again, let's see, I must have typed something in wrong. Oh, I know what it was. That -36, it doesn't like minus, it likes negative. -36, it thinks it's a subtraction problem. So again, let's get back up to the top. We're at -6. And so what am I seeing this time? Again, I'm only looking at positive and negative numbers. But notice negative, negative, and I should be over here. Negative numbers everywhere. Negative, 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 negative. That means the slope is negative. It's downhill graph. And all of a sudden, there's a transition right there to positive. It was negative, and then all of a sudden it's positive, 0.44. Well, what's right there? Oh, negative 1.58. Remember how that was the x coordinate of the minimum? So I can see it's negative, and then all of a sudden it's positive. And so how long is it positive? Well, there it's a switch right there, negative 2.16. The x coordinate of the maximum was 1.58. You see what I'm saying? Like you could actually never graph this and yet understand its behavior by looking at the first and second derivative. So that's just kind of cool. I mean, you need a table, you need Excel to kind of print out a bunch of these, and it'd be even better if we went back to table set, instead of saying this thing is going to increase by 1, we could increase it by, say, like 0.2 or something like that. And unfortunately, that means the table is going to be it'll have a lot more values. But notice how you can see that. Notice how you can see the negative 1.58 here a little better now. See how it was negative, 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 and then there was a transition to positive. And so, the transition was right between negative 1.4 and negative 1.6, maybe around negative 1.5. I can actually see the maximum or minimum happening right here. Negative slope switches to a positive slope. That's just kind of cool. So again, what I'm talking about is just analyzing a graph, doing this analytically. We have better methods. We have graphing calculators and so forth, but it's just kind of cool to use your brain, stretch that muscle, flex that muscle. So now, of course, the big payoff pitch here is let's go back to Desmos and actually turn the graph on. Would it be really satisfying on a test is to go turn this graph on and then bam, their whole graph is, really going through this. Let's make it green so it's at least a different color. It's like, ah, sweet. That totally verifies I didn't do anything stupid, which is a miracle. So sure enough, those 5 points allowed me to know a lot about this graph, even though it's a really complicated graph. Now, let me just say one thing that's kind of interesting here. You get back to this concept. If you let x be time, and you say, well, it makes sense that time is bigger than 0. So this is the only part of the graph you actually care about. This type of equation does an excellent job of modeling, say, drugs in the bloodstream. So if you're in the health industry and you pull up, I got a son-in-law who works for Mercy Flight, so he pulls up on people who are OD'd laying on the ground and checks their pulse and all this stuff. Notice this is how drugs in the bloodstream would behave, alcohol in the bloodstream or drugs in the bloodstream. And for that matter, anything. You get stung by a bee and you have an anaphylactic shock reaction to it. And so, there's this coursing through your body. Anything you introduce to yourself, even food. I ate a candy bar. I saw sugar in the bloodstream. It doesn't have to be a negatively connotated situation like drugs or alcohol in the bloodstream. But notice that red dot would be real important because that'd be your maximum concentration. If I go back and turn some of those labels on, and we'll pretend for a second that those are times, and let's say hours, even though that doesn't make much sense. But what does that first inflection point mean if this is drugs in your bloodstream? So 0.72 hours later. And
Would that be example of the halfway point before it starts going down?
Yeah, in reality, up to that point, the rate at which the drugs are increasing, it's actually getting more and more and more into your bloodstream. But at that first inflection point, it begins to kind of level off. So it's like it's still increasing. It's increasing all the way to the red dot, to the maximum. It's still increasing, but it's not increasing as fast. The rate at which it's increasing begins to slow down after the first black inflection point. And then it levels off until you hit, let's turn this point on now. Where are you? Why isn't that green point? Why doesn't it exist? No, it just didn't show up because it wasn't on the the graph. So it's beginning to level off here, and then it reaches a peak, and then it starts to drop. And then that second inflection point means the rate at which it's dropping is actually increasing now. So it's actually dropping at a real precipitous rate. And so one thing that's really cool to know, and it turns out somebody in the 8 o'clock class is actually was in the medical field, and they said when somebody comes in, because they worked in an ER or something like that as a nurse, or not a nurse, but a orderly or somebody that kind of helps out. But it's like they actually have all this. This is a known thing. I don't know if it makes sense to you, but if you, I don't know, let's just say you got stung by a bee and you actually kept track of, you actually collected data points, and this is what Eve said earlier. Could you work backwards from data points to create the equation that modeled this? Yes, and that's been done scientifically. Are you the person that could do that? And keep in mind, this isn't even just like drugs or whatever in the bloodstream. This could also be like it rains and the river level comes up to a peak and then it levels off and kind of flattens back out again. Like this is models so many things. And so to be able to take your own data points, you just measured how deep the river was at a number of different points. You know, would you be able to recreate using regression? Would you be able to recreate? Would you be able to start with an equation that wasn't 18x over 2x squared minus 4x plus 5, but ax over bx squared plus cx plus d, and use regression to find the equation that actually modeled the particular patient that was in front of you, or the particular river that was out in front of your house, and actually make this equation for yourself. In a sense, that's what's been done with drugs in the bloodstream. So when somebody comes in, you can actually say, when did they take this drug? Oh, it was 2 hours ago. And then they can say, oh, okay, I know what's going to happen to them. And of course, when you get out to here, you know, now it's out to where you're safe. Or let's do something practical. Like maybe you have a beer. And so like, should I drive? Well, you know, what's the point at which it gets down to where you're kind of at a level where you're kind of back to safe again? You know, where's that line? I mean, can you do that kind of stuff? Like, can you use your knowledge of algebra and calculus now to actually be the person that creates these kinds of functions and understands how to analyze them? And you can see that calculus is just one more cool thing that you can add to your understanding of your algebra knowledge. And so it's just kind of a powerful thing. You know, I think it'd be fun. I wish we had time to come up with something that would behave this way. Maybe, you know, maybe we'd have to have too much technology to measure drugs in someone's bloodstream, and maybe it wouldn't make sense to put drugs in someone. But, you know, could we have somebody eat a candy bar and then do the little pinprick, you know, like for your glucose level, since diabetics have that? Like, would it be possible to eat a candy bar and then, you know, every whatever 30 seconds, you know, and take a blood glucose concentration, and, you know, to actually do this? I mean, that's what kills me when I teach math, is to be able to completely analyze that. That sounds like an awesome project, but, you know, how are we going to get a hold of a glucose and meter, and, you know, how hard is that to do? And does somebody have to get pricked like 40 times? And, you know, who has the technology? I mean, is there a way we can do that? I mean, to me, that's where math gets fun to me. This is great to find maximums and minimums, but if we could actually go get our own equation based off data like this, that sounds awesome. Anybody diabetic? Can we poke holes in you and do this for a project? Kidding aside, if somebody could think of a way that we could, to me, this would make a good project at some point. I have other projects that I've already designed for the rest of this class, but if anybody can think of a way that with little technology, we could actually just sit on a Zoom and collect data like this. I don't care if it's me. If I had a glucose meter, I don't know, maybe I'll find out about that. But if there's any way we could collect data on something that would kind of ramp its way up like this and reach a peak, and then it would kind of leak back out, that'd be awesome to actually do that. And I bet most of you couldn't do the regression. One of the things that's extremely cool about Desmos, by the way, is your calculator has a very limited number of equations that it'll come up with, but in Desmos, you can actually make your own equation up. If you know that this is a decent model right here, like a linear equation over a squared equation, Desmos will go find it. I'm kind of making this up. I've seen in books that this is a model, but I actually don't believe it. I'd love to just go collect my own data and try this out for myself, and then maybe we conclude it's not a very good model and there's a better one, and now we got another problem on our mind. Is there some way we could come up with a graph that looked like this, that was better?
This
better
like a
model
more
than that?
complicated chair equation. Because I remember in the chair equation you said you could use linear algebra. So wouldn't to find this, won't we need linear algebra?
That's only if you go in the background. Like the cool thing about Desmos is if you just type in your data points and you say, I want an equation that looks like this, except for you put A, B, C, and D in here, it'll actually go find them for you. And so, yeah, it's linear algebra that's in the background, but that's already programmed into this machine, which is what I think is so cool. So what I'd really love is just to get the data. Like if you know somebody who's diabetic, and actually, is that reasonable to test somebody? And how often do we need to test them? Is it every minute, or is it every 2 minutes? Is it every 30 seconds? And would that just destroy them? Or does it cost a lot of money? Like to use the little, I know there's a little machine, just kind of put it on you. So, but there's other things we could measure. Pulse. What if we like put you in a cage with a bear and we check your pulse? Anybody want to volunteer for that one? And you're like, freak out. And then, your heartbeat begins to slow down as time. Like, you see what I'm saying? Like this would model all kinds of things. We need to scare one of you and keep track of your blood pressure. I don't know. That'd be fun to play with. I don't know how to.
I have a friend who has one of those constant monitors for their blood sugar. I could ask them if they'd be willing to share like a daily reading or something. Like
that'd be awesome. I mean, all I really want is the data. It'd just be fun if it was actually real, because I kind of hope it doesn't come out nice. It'd be fun to play around with it. But yeah, if anybody has any way to get any data like this, and I don't want it offline. I want to literally get it from somebody. I want to measure it ourselves. It'd be ideal if we could do it live right here in class, if you will. But like that's how you get paid to know math. Do you see what I'm saying? Like, are you the person that could help somebody actually monitor this? That just sounds awesome. Please do, Jesse, if there's a way you could actually get real data from this person. We don't have to watch it happen, but at least the fact that it came from somebody, I think would help. And obviously, I don't know how that works, because we'd want to introduce a candy bar to them, if you will. It's like somebody who's diabetic, you can't just screw around with them like that. It'd work better if we had her machine, but we did it on one of us, if you will.
I could ask them to, like, when they have a meal, like show the readings like
exactly
from the points before the meal to like sometime after it.
Exactly. That would be awesome. That would totally work. Yeah, a meal would work. And so they eat whatever they eat and off we go. Great idea.
I thought you were going to say my friend has a bear, and I was a bit disappointed when it wasn't.
My friend has a bear. Okay, we got a bear. All we need is a volunteer.
Kind of friends you think I have, but no bears.
How about jumping off a bridge? There's a good one. You don't need a bear. Let's jump off a bridge into the water.
Don't you run the river a lot? Don't you have like jumping rocks or something?
I know a whole bunch of them. All we need is the volunteers. The problem is I can't do it because I'm not going to be scared. We need someone who's really afraid of it.
Well, I think that's the thing, is it'd be more effective if you pushed someone, as opposed to like if they volunteer, they're not going to really have the effect.
Exactly right. So
yeah, I can't swim, so I'm going to be terrified either way.
Okay, you just volunteer. That's perfect. So we'll have everybody stand on the bridge and with the blindfold on, and then I'll push one of you. And probably it'll be Cheyenne.
We'll need life jackets.
No, we'll take care of that stuff. We'll have a scuba diver down there to get you or whatever. We can work this out. But for you future teachers, I mean, I don't know. Do you find yourself thinking like a lot of the things that we've done are kind of boring, but it's like, yeah, that would be worth a couple of days, like to literally, get together and go run an experiment. I don't know about you, but that just gets me all excited. Like, wow, that's cool. We could actually use this for something. And again, I don't have a great deal of confidence that this is actually going to be a perfect model. I've never played with this before, so I'd love to do that. So we've, if you will, burned the whole period looking at that example, which is awesome. I have two or three other examples. I'd really like just to play with this in practice, but if I start this, we're not even going to come close to finishing the next one. So maybe I will, I'll give this to you as an extra credit question. So let me see. just so that this is in the notes, I'm going to go back up here before I give that to you. Yeah, that was a mistake.
So on the test, we're not going to be given any second derivative with cubed equations, right?
Yeah, I got to be really careful. Like I can't give you this problem on a test because it's just too involved. Like, you know, I don't want a cubed equation. I got to make sure you have like a maximum and a minimum, because you can solve squared equations. So you can have one max and one minimum, and you can have two inflection points because that's solving a squared equation. So I want it to be interesting enough that you find yourself saying, like this problem, I think, you find yourself saying, calculus really gave me something here that I would not have been able to do without calculus. But not as interesting as this question, because I don't want there to be too many points to find. So actually, I have a question we could probably squeeze in here real quick. We have 15 minutes. Let's do this one. I gotta go. This is an example of kind of an easy one. So I think I'll go down here. I'll copy that graph onto the notes before I leave class. So let's just look at this. This is kind of a cool one because it's simple, and also because you would say, like the last problem, you have no idea what the graph of this looks like. And again, I had to work pretty hard to find examples like this. But let's just do this quickly. Let's do this quickly. So what's f prime? And let's try to analyze this entirely just with a graphing calculator. We never even look at the graph. So what's f prime of x? You say, oh, that's product rule. The derivative of x squared is 2x times natural log left alone plus x squared left alone. What was the derivative of natural log again? You should probably have to look at your notes. Maybe you have a good memory.
Isn't it 1 over x?
Yeah, it's 1 over x. So there's the derivative. And so that's kind of nice because it cleans up a little bit. So you could say that f prime of x is equal to, can't do anything with 2x natural log of x, but x squared over x is just x. So again, I find it worth mentioning that that's a nice simple derivative, because remember I have to take a second derivative later. So that helps me have something to look at. Now I want to set that equal to 0. And the question is, you know, how terrifying is that going to be? How taxing is that going to be on my brain algebraically to solve? Well, you got to be a little careful with this. If you subtract x from both sides and divide by x, the x will drop out. But it's actually a little better to notice, hey, both of these have an x in them. That's a little better. And the reason that's a little better is because x is 0 is one of our answers. And if you divide both sides by x to solve this, you will lose that one. But x is 0 is one of our answers. So I have junk times junk equals 0. So if x is 0, that one will give me an answer. And then I got to figure out when 2 natural log of x plus 1 is equal to 0. So I'd subtract 1 and divide by 2. So the natural log of x would be -1/2. Algebraically, how do you get yourself out of that mess? Do you still remember that? My guess is not automatically, but how do I solve for x? How do I get rid of natural log?
Would it be something with e?
Yeah, e's involved. E's involved. By the way, if you look on your calculator, the way I survived college not knowing algebra really very well at all, I just said, oh, how do you get rid of natural log? Second natural log on my calculator. Look on your calculator. If you hit second natural log, what do you notice is behind there? What's behind that button on your calculator?
E to the x.
E to the x. In other words, the next move for this is x is e to the -1/2. Or that'd be kind of cool to write it as 1 over the square root of e. Notice it's kind of cool that you can nerdily get the exact x value for this. Now, it isn't terrifying to go back and, you know, figure out what f of 0 is. So for this answer, f of 0 is 0 because 0 squared times natural log of 0. So that's 0. So 0 is a maximum or a minimum. And then I got to go put 1 over square root of e in. I want to figure out what that is as a decimal, so I'll write here approximately. I'm just going to type e raised to the negative 0.5. Again, I think you should be capable of doing this exactly correct, but approximately is just fine. So I'm going to take that number and square it and multiply by the natural log of it. So 0.61 squared times the natural log of 0.61. Notice that isn't that tough to type in. I got negative 0.18. So f of 0.61 is approximately negative 0.18. So now I can conclude that I found some maximums and minimums. I don't know which is which yet, but I know I've got one at 0, 0, and another one at 0.61, negative 0.18. So that's huge. So let's graph that. That's not what I wanted to do. Man, this is cool. So thinking bigger graph paper would be better, because these are pretty small numbers. I'm wasting too much time. I gotta speed up here. So, okay, cool. So where's these points? Where are these points at? Let's graph them. So 0, 0 is obvious. That's true. That's a maximum or a minimum. And then 0.61, so a little over half. And so I'm going to make each of these worth 1. So there's 1, there's 1, there's 1. So a little past halfway and then down just a hair. So I'm saying like right about there. So let's see, how could that be? What could be going on there? One's a maximum, one's a minimum. Again, I find myself thinking just logically, most likely, I guess you could say that, the max is on top and the minimum's on the bottom. If that's the case, does it make sense there's going to be an inflection point right there? Like between there, the transition? But let's let the algebra, speak for itself. Let's not jump ahead of ourselves. Let's try to entirely own this thing based on our knowledge. And so let's go get the inflection point. Inflection point is where the second derivative is equal to 0. So now I look back at my first derivative. Let's copy it down below. And let's go find the second derivative. So the second derivative, I see a multiplication here, so I'm thinking product rule. So the derivative of 2x is 2 times the natural log left alone, plus the 2x left alone times the derivative of natural log of x. So there's a product rule. And then I love plus signs because I just ignored that x until later, and the derivative of that is just 1. So to clean that up a little bit, 2 natural log of x, I can't really clean that up, although you could write natural log of x squared. And then 2x over x, the x's cancel, so you just have 2, and then 2 plus 1. Okay, so it's 3. In fact, that's the second derivative. Again, interrupt if you want me to go a little slower. And again, of course, I'm concerned with when is that equal to 0? So when is this equal to 0? Well, I'd subtract 3 and divide by 2. So the natural log of x equals negative 3 divided by 2. So x equals, there's only one. There's one inflection point. Notice this is kind of cool. There's only one. So x equals e to the negative 3 halves. And I'll just leave it at that. My calculator says e raised to the negative 1.5 is approximately 0.22. And so I need to know the y that goes with that. In other words, find the ordered pair on the graph. And remember, the original equation was x squared natural log of x. So I'm typing 0.22 squared times the natural log of 0.22. And I got negative 0.07. So I then conclude that I have one inflection point at 0.22, negative 0.07. So there's only 3 important points on this graph. There was a maximum and minimum, or maybe 2 maximums or 2 minimums. And then there's one inflection point, 0.22, 0.07. So let's go back at the graph and stick 0.22, negative 0.07. And so sure enough, it is right in between those. So if this is all I have, then I'm thinking, let's see, this is a maximum and there's a transition right there to concave up. And so maybe it looks like this. It's like a cubed equation, maybe. Is that true? There's no more inflection points, so that means this doesn't turn down. Does that make sense? That's not true.
I can't see any other way you could graph it.
Yeah, and yet it feels like, first thought you should be like, what? That's a cubed equation. Well, all curves aren't the same. It looks kind of like a cubed equation. That doesn't mean it is cubed. But it's kind of has that look to it. Let's go look at Desmos and see what Desmos saith about this graph. So x squared natural log, that's not where natural log is, it's under function. I think I can just type ln for natural log, but I'm just gonna go find it. Log, there it is, natural log of x. So there's the graph. Is that right? Is that what we just found?
Why does it not go negative?
Yeah, how come there's no graph to the left of the y-axis?
Because it's not possible for it to even approach 0, I think, technically, right?
Well, it's because of the natural log. If you try to take the natural log of a negative number, the answer is There's no such thing as a natural log of a negative. And again, this is why in an algebra class you bore yourself and don't understand why you talk about domain and range. Like, what's the domain of this function? Well, x can't be negative. It's kind of like a square root. If you take the square root of a negative, not going to happen. There won't be a graph to the left of the y-axis for a square root graph. And that's true for natural log as well. If you want to ask me after class, like, we'll play around with that for a minute. Like, why is that? Why doesn't it work? I mean, you could get your calculator out and take the natural log of -2, and it's just going to say, But that's why. But notice it does, and this is kind of cool, but notice calculus tells us something here. Like, does that actually leave 0, 0 flat? Yes, it does. Like, that's actually flat. The slope is really 0 right there. That's kind of cool. And then it hits this transition, and I don't know, what do you think? To me, maybe right in there, right about there. Would you agree that looks like the transition between concave down and concave up? Now, we just said a second ago that we thought that was algebraically the 0.22, negative 0.07. Notice my guess wasn't accurate, but at least I was in the ballpark. So again, that's kind of cool. That's where the transition is between concave down and concave up. So, in a sense, part of you should say, well, I guess this is good because that looked like a cubed equation. And now it doesn't look like a cubed equation because natural log didn't let the graph exist on the left side of the y-axis. And so sure enough, the left side of that blue dot, it's concave down, the right side is concave up forever. So that's what inflection points do. It means there's only 2 definitions to this graph. It's concave up and concave down. That's it. There's only one division there, so 2 sides. And there's one maximum and one minimum here. And so, again, I'm not really satisfied personally unless I look at the graph of this, but algebraically, it wasn't terrible to find these points. And so that's kind of cool. Comments, thoughts? -0.61, -0.18. So notice that's working. How come it actually doesn't hit? What did I do wrong?
We estimated, it's not the exact number.
Yeah, we rounded. That's why it's nice. It's good practice to say approximately, just to tell yourself and other people. But notice I rounded to 2 decimal places. So if you're zoomed out at least reasonably, then it looks fine. It looks like it's okay. So that's cool. It does behave exactly like it should have. Calculus did allow us to understand what this graph looks like, and all we need is inflection points. Only had 3 ordered pairs. And if I remembered that natural log can't be negative, then I never even would have bothered drawing in the left half of that graph. But I'll be honest and say I didn't remember that. So that's kind of cool. All right, I think that was a good use of time. Do you want an extra credit question? No, guess it doesn't matter. I'll just give you one. I gave you 2 extra credits today. One of them was go figure out the history of cubed equations. But here's this one isn't terrible. This is not terrible. Extra credit. This is good for practice. Graph. Like find the graph of this. Find the inflection points. So that by that I mean inflection points and max mins, or what your book would call critical points. This is kind of an interesting one. What if it wasn't e to the x, but what if it was e to the negative x cubed plus 4x squared minus 5x minus 2? So it's e to junk. Do you see chain rule? Derivative of e to the junk is e to the junk times the derivative of the junk. This is kind of a neat one. And of course, you should look at this and think, I have no idea what this graph's going to look like. But to what extent can you analyze this graph without cheating? Like how sure can you be that yeah, it's definitely concave up here, definitely concave down there. I'd encourage you to do as much as you possibly can to convince yourself that what you think is the approximate graph through these critical points, however many there are, what you think is right is actually right, so that you don't go to Desmos going, I really have no idea if this is right. Try to use your algebra and calculus skills to be sure. All right. Your brain is now ready for the real world. I'm going to stick these 2 graphs into the notes. Close that one. Yeah. All right. I'm happy. Okay. You have a weekend upon you. Let's see. What are we doing next week? Oh, we're applying this to optimization. This is kind of cool. Business example, 4.5. That's kind of cool. What's the biggest rectangular box you can make out of a piece of paper or stuff like that? It's kind of neat application for derivatives. All right. Stay after, ask questions, or get yourself out of here.